Welcome. Now, I'm aware that you folks have the technological ability to take that screen and make it a full screen, the board there. So I've written quite a bit of stuff on there. It's more or less legible, about as legible as my scrawl ever gets. But I'm going to go through it reasonably rapidly. These theoretical approaches to energy and energy dispersion are illustrated. I have several illustrations that I'll go through. They're not dwelled upon a lot in a survey course in general chemistry, but they're mentioned, and I want to make sure you get a fairly decent coverage of all the fundamentals. So we start with the first law of thermodynamics. And it says that energy in the universe is constant. Nothing particularly complicated about that. All the energy in the universe is constant. Now, energy can be converted, but it cannot be destroyed or created. In other words, the acceptance of this theory is that in the whole universe, there's X amount of energy, and that's the way it's going to end. It can be converted, changed from one to the other, obviously condensed into matter. Okay, let's talk about the different kinds of energy relationships. An exothermic relationship, energy flows out. You light a burner. It's an exothermic reaction because the propane, butane, methane that you're using exerts energy. So that is an exothermic reaction. Endothermic reaction, energy flows in. A variety of chemical reactions when you put things together that cool off the central composition. That means that energy flows in, basically. All right, up here we have delta E, up here, which is equal to Q, which is heat, plus W, which is work. I should, again, tell you to get some cards and keep up with these things. Just because a card on thermodynamics and thermal energy covers a very wide area, but doesn't cover, doesn't require a lot of cards. So now pressure is equal to force in an area, or force over area, if you want to think of it that way. Work is force over a distance. Distance is illustrated by delta H, which is change in height. Moving something is a change of distance. All right. Playing around with that, you could say that work is equal to pressure times area times the change in height. Or pressure is the change of volume, since area and change of height would comprise volume. Here's one you got to know. So write it down, big letters, joule. I mentioned it before. A joule is a kilogram meter square per second squared. We'll talk more about that later on. There's a prescribed amount of energy needed to change the temperature of a solid, liquid, or solution. This is basically the specific heat of that substance. Water specific heat is 4.183 joules per gram centigrade degree, and you must know that. That's absolutely necessary that you know it. So memorize it. There are very few things I tell you to memorize in this course. Now you need to memorize. Okay, let's do a problem. Work to change an ideal gas from 46 liters to 69 liters at constant 15 atmospheres pressure. So your formula would be work is negative P pressure times the change of volume. The pressure is 15 atmospheres. The volume is not actually known. The work or the volume is known as 64 minus 46. It's given in the problem. 64 liters minus 46 liters. So if you multiply that out, you come out with a negative 270 liter atmospheres. Why negative? Because it's being given off. If it was positive, it'd be brought in. All right. Back to preservation energy changing from solid to liquid, the so-called specific heat. Enthalpy, Enthalpy, is H equals to E, system's internal energy, times PV. And the volume will be at under both systems. So delta H, the energy of the system, is equal to change in energy plus the change in PV. With the pressure constant, delta H would equal to the change in energy plus the change in volume. Now, if energy is given off, it's called an exothermic reaction. If energy is absorbed, it's an endothermic reaction. Those you need to know. That's two definitions in this material that you really need to know because you'll use it from now on. Exo, given off, endo, brought in. Okay, example of the type of reaction. If you burn methane with oxygen, you get carbon dioxide and water vapor. That's what heats your house in a lot of cases. Now, for 1 mole of methane, the energy given off when it's burned is 890 kilojoules. The question asks, calculate the delta H for 5.8 grams of burned methane. Well, you got 5.8 grams of methane, and of course you got to change everything to moles. Remember that with all these problems, you got to change everything to moles. Well, mole of methane is carbon, which is 12, and 4 hydrogens, which is 4. That's 16 grams per mole. So you take your 5.8, divide it by 16, and give you 0.36 moles of methane. Multiply it times the given factor of energy per mole for methane, which is a negative 890 kilojoules. So when you burn 5.8 grams of methane, you exert or provide 320 kilojoules of energy, 1,000 joules if you want. All right, more specific heat. Specific heat, as I had mentioned previously, is joules per gram times centigrade degree, or joules per gram times Kelvin, because relatively speaking, it's used about half and half, depending on the problems. C, big C, is always the heat capacity. And this is found by finding the heat absorbed and divided by the increase in the temperature of the system. Okay, how does that work? Well, let's do a problem. The example problem is 50 milliliters of 1.0 molar hydrochloric acid, again, stomach acid, reacting with 50 milliliters of 1 molar sodium hydroxide. Now, you already know what the products are. We've had the same reaction several times. Hydrochloric acid plus sodium hydroxide produces salt water. But by definition, if you have a solution of hydrochloric acid and a solution of sodium hydroxide, by definition, you have 50-50, you have 100 milliliters of water, in essence. And you know what the specific heat of water is? I just made you memorize that. It's 4.183 joules per gram centigrade degree. So if you multiply that out, you get 4.18 times 100 times the change in temperature, which is given as 6.9. I guess I didn't finish the problem, my bad. When you pour these two together, and stir it up in a styrofoam container, the temperature increases from 25 degrees to 31.9 degrees centigrade. So the change in temperature is 6.9 degrees. Okay, so to find the solution, you multiply the specific heat of the 100 milliliters of solution, which is the same as water, 4.183 joules per gram centigrade degree. And then you multiply that times 100, which cancels your grams out, and then times the change in temperature, which is 6.9 centigrade degrees, which cancels out your centigrade. And all you're left with is joules. And that comes out to be 2.9 times 10 to the third, 2,900 joules. That is your problem. Now, I know some of you like more exotic problems, so I throw in an exotic one here. Changing graphite to diamonds. Now, years ago, I would have been criticized for doing something like this because it's so impractical. But ask any jeweler, especially a big-time jeweler. He'll tell you flat out, every year they're getting better at making diamonds of a quality that is as good or better than nature does. Now, they're expensive, but they still can make them. So this is more practical than it was decades ago. So graphite solid changed to diamond solid. Well, in order to do that, you got to accept some energy relationships. To vaporize graphite, to burn graphite if you want, it's a negative 394 kilojoules. To burn diamond, who the heck ever wants to burn diamond, but if you want to burn diamond, it's negative 396 kilojoules per mole. Now, first thing you got to do is change your graphite to gas. Well, graphite times oxygen means burned, forming carbon dioxide, which, when superheated and super pressure, will condense to diamond solid, and oxygen is given off. And the amount of energy needed is 2 kilojoules per mole, making this an endothermic reaction requiring energy to form the diamond. Duh, you already knew that. But I thought that was kind of an interesting illustration of where the practicalities of this have come full circle over the decades. Years and years ago, it was possible and was done industrially. They used to produce diamonds even as early as the 60s. I don't know whether you guys get these annoying survey calls, but I've seemed to have attracted a lot of them the last few months. Anyway, as I was saying, in the industry, they used to make what they call diamond flakes, and they would put them on wheels and use them as diamond grinders and glue them with epoxy on blades so they could have diamond blades which would chew through any metal. And that's been around a long time. And they've started, back in probably early 90s, they started making small gemstone diamonds. But now, heck, they're turning out 2 and 3 and 4 carat diamonds. And my jeweler friends say that, wow, the quality is almost so good that you can't tell the difference. And the price is going down because as technology improves, it tends to drive the price down. So anyway, if you want to burn a diamond, here's your formula. Okay, the next thing on the abbreviated word for this section is Hess's law. And Hess's law says that change in enthalpy from reactant to product, same if it's done in one step or multiple steps. In other words, if it's a multi-step reaction, such as the graphite, changing it to diamond, that's a multi-step. So the energy, which we found out was 2 kilojoules, whether it's one step or 2 or 3 steps, it always follows Hess's law. Now, the change in H, or change of energy of formation, if you wish, or the change of energy of decomposition, is all accountable. You must always account for every gain or loss of energy and mass. If you don't, your reactions are incomplete. And it's always advisable to be complete in your energy reactions. And the last of the list here is enthalpy of composition and decomposition accounted in standard states. So enthalpy will make methane if you wish, and the decomposition will exert energy from its decomposition, but they're identical. Same amount of energy needed to form something as it is to decompose it. And if you keep that in mind, there is no gain or loss. It always must be accounted for. Then you'll do well with your energy relationships. Okay.